Hello, today we're continuing in our series on A-level physics revision, building on the information we learned in the videos on circular motion and friction. And we're going to be looking at a subject which is included in some A-level equivalent courses on banked turns. I first need to remind you what we learned from the video on friction. If you have a heavy block on the floor, such as a bookcase, which has a mass m, then from its centre of mass it will exert a force downwards, mg. And there will also of course be a normal force acting upwards, and the normal force always acts perpendicular to the plane of the surface. Now, if you attempt to move that bookcase by applying a force, let's just say initially a small force, to push it to the right, of course you know it won't move. And the reason it won't move is that there is a frictional force, which is the friction between the bookcase and the floor, which we'll call Ff. And that frictional force always moves in the direction to oppose the movement you're trying to achieve. So you push it in that direction, but the bookcase has frictional force which resists that force and pushes in this direction. And as you increase the force against the bookcase, so the frictional force increases. It's called a non-conservative force. It's always exactly equal to the force that you're pushing, subject to the fact that there is a maximum frictional force. And when you get to that maximum frictional force, that is the last point at which the bookcase can resist movement. If you increase your force to exceed the maximum frictional force, then the bookcase will start to move in that direction. And the maximum frictional force is given as the coefficient of friction, which is mu, times n, which is the normal force. And in this particular case, you can see that since the bookcase is not going to accelerate up or down, the net force in the vertical direction must be 0. And that means that n must equal mg, because n is going up, mg is going down. They must be the same so that the net force is 0. And so we can see that the frictional force maximum is going to equal mu mg. So when your force against the bookcase exceeds mu mg, the bookcase will begin to move. Then the next thing I want to ask is, what makes a car go along a road? In other words, what drives it forward? Here's my car. Here am I driving. And the question is, what causes it to go forward? And you might say that the answer is the engine, which is usually underneath the bonnet. But that's not strictly true, because all the engine can do is to cause the wheels to turn. If this were a frictionless surface, if this were sheet ice, all that would happen is that the wheel would go round and round, but the car would not go forward. The reason that the car goes forward is because of friction between the surface of the road and the surface of the tyre. What is happening is that the wheel is spinning in this direction. That is causing a force in this direction, and that will result in a frictional force in this direction, and that's what causes the car to go forward. It is the friction between the tyre and the road that causes the car to move forward. The engine turns the wheel, but if this were frictionless, sheet ice, nothing would happen. It's because there is a frictional force that causes the car to move forward. So now let's suppose this is an overhead view and I'm travelling in a straight line, and here is my car, and my wheels, of course, my tyres are pointing in the direction of travel. And at some point I want to go round a bend. And that will be an arc. It will have a radius, r. And when I get to this point here, if I want to turn, I'm going to have to turn the wheels so that they are in the direction that I want to turn. Now, Newton's first law tells us that a body will continue in its state of rest or uniform motion unless acted on by an external force. So this car ought to continue to go straight ahead. And indeed, if you were on sheet ice and you turned your wheels, it wouldn't really matter which way you turned your wheels, the car would continue to go ahead. That would be called a skid. So what causes a car to go round the corner? Well, the answer is friction again. And what is that friction? Well, remember that Newton's first law is trying to make your car continue in a straight line. So there is, if you like, a tendency to want to continue to move in that direction and not go round the corner. So there must be a friction on the road surface which acts in this direction, and that, as we've seen, is Ff. That's the frictional force, and that force is going to be equal to mu times the normal force, and as we saw with the bookcase, that can be written as Ff is equal to mu times the mass times g. But what is that frictional force providing? That frictional force is providing the centripetal force that gets you to go in, we'll call this a circle, an arc of a circle. And from our video on circular motion, we established that the centripetal force, which is provided by this frictional force, is going to be equal to mv squared over r. This frictional force here, incidentally, was the maximum frictional force. And so consequently, the frictional force is providing the centripetal force, and so you've got that mu mg, which is the frictional force, the maximum frictional force, is going to be equal to mv squared over r. You'll notice that the m's cancel, and that gives us that v squared is given by mu rg. So the maximum velocity, because this is the maximum frictional force that can be provided, the maximum velocity with which you can turn round that corner is given by mu rg. And what does that tell us? Well, g is a constant, so you can't do anything about that. Mu is the coefficient of friction between the tyre and the road, so the greater the coefficient of friction, the greater the speed that you can go round at the corner. And the greater r is, the faster you can go round the corner. So if r is a small curve, then you can go round quite fast. If r is such that the curvature is very large, then you'll need to go much slower. If you exceed this maximum speed, the maximum speed that friction can keep you going round that curve, then all that will happen is that you'll skid off and hit a tree. So you are wholly reliant, when you're travelling on a flat road, you're wholly reliant on friction to get you to turn round corners. So the question now is whether it's possible to go round a corner without being reliant on friction, and the answer is yes, there is. If you take a circle, cut out a circle in the middle, and just cut it at one point, and then make a cone. This you'll see is, this would be a cone if I hadn't cut out the circle. As you can see, it's now a banked curve. A banked curve. The black line represents a route, and what I shall show you in a moment is that if this were a road surface banked up in this kind of way, I would be able to drive at a certain speed around that black line without needing frictional forces at all. I could do it even if this were made of sheet ice. It would still work, and I could continue to go round that circle at a constant speed, and I wouldn't skid at all. And I'll demonstrate why that is the case. It is called a banked turn, and the way it works is that here is the bank at an angle theta to the horizontal, and here is my car on the banked turn. Now the car, remember, has a mass, so the weight of the car acting down will simply be the force mg, and there will be a normal force which always acts perpendicular to the road surface. We'll call that n. And you can always, of course, resolve that normal force into its component parts, a vertical component and a horizontal component. If this angle here is theta, then it's pretty easy to show that that angle there is also theta. And if that's the case, then the vertical component will be n cosine theta, and the horizontal component will be n sine theta. And since I'm not interested in frictional forces, because I am alleging that this can all work without frictional forces, that's all there is. So let's now examine what is happening. Firstly, let's think about the forces in the vertical direction. Well, the car is neither accelerating up nor accelerating down, so there must be no net force in the vertical direction, because force is mass times acceleration, and if there were a net force, then the car would accelerate in the vertical direction, and it plainly doesn't. So the net forces in the vertical direction must cancel out. So that means that n cosine theta, which is the force acting up, must equal mg, which is the force acting down. Now let's have a look at the forces in the horizontal direction. Well, there's just one, n sine theta. Well, what is that doing? That is providing the centripetal force that will keep my car going round that circle that I showed you a moment ago, the black line of the banked turn. So that's providing the centripetal force, which of course is mv squared over r. Now from this formula here you can see that n is mg over cosine theta. That is n, mg divided by cosine theta. So if I put that into this formula here, I've got n, which is mg over cosine theta, times sine theta, is equal to mv squared over r. The m's cancel. Sine theta over cosine theta is of course the tangent of theta, and that gives you that v squared is equal to, bring the r up here, you get r times g times the tangent of theta. And what that says is that you can travel round that banked circle at a speed v, where v will be determined by the radius of that circle. The bigger r is, the bigger the circle, the bigger v can be. And the bigger theta is, the bigger the angle to the horizontal, the faster you can go. So as you increase theta, you can increase the speed. But this is the actual speed that you must go round that circle if there is to be no friction. If you go any faster, then you will simply go sliding off the top of the bank. And if you go any slower, then you will slide down the bank. Of course, friction usually does apply, so friction to a certain extent will stop you doing either of those things, but only to a limited extent. But if you've got no friction, if this really is sheet ice, you must travel at that speed. Any faster, you go shooting off the top of the bank. Any slower, you slide down the bank. And just let's look and see what happens when theta is 0. That is when the road is flat surface. It's actually just horizontal. When theta is 0, the tangent of theta will be 0, so the whole of this term becomes 0, which means v is 0. So what that is saying is that without friction, if you're not reliant on friction, then you cannot actually turn a corner on sheet ice, because any velocity will be too much and you will end up in a skid. So you're wholly reliant on friction when you turn the corner when the road is absolutely flat, which of course is what we showed just a little while ago. But of course we know that friction does apply. Road surfaces are generally not made out of sheet ice. So let's just review what we said before. You're travelling along the road in this direction and you want to turn a corner around an arc of a circle like that. Newton's first law says that you will continue in your straight line unless acted on by an external force, and in this case it will be frictional force that provides the centripetal acceleration and the centripetal force. So what is the car preferring to do according to Newton? It prefers to continue to travel in this direction, and therefore there will be, as it were, a tendency to move in that direction. This is sometimes wrongly called the centrifugal force, implying that there is some kind of force pushing you outwards. Actually, that's not true. What is actually happening, of course, is that Newton's first law is applying, And Newton's first law simply says the preference is that the vehicle will continue to travel in a straight line. So there is a preferred intention to do that, and you are actually having to force it to travel in this direction by providing a force, which in this case is a frictional force, to get you to go round the corner. Consequently, the tendency when you're on this ramp is to go outwards in order to continue in a straight line, which means that friction must apply in this direction, down the ramp, and of course friction is always between the car and the road and acts along the surface of the road. And once again, that frictional force can be resolved into a horizontal and a vertical component. And if the frictional force is Ff, then I think you can see that since this angle is theta, this angle is going to be theta here. And so the frictional force, which is horizontal, is going to be Ff times the cosine of theta, and the frictional force, which is vertical, will be Ff times the sine of theta. So now we've got two more forces added to our diagram, the horizontal and vertical frictional forces. So now we do exactly what we did before, and we look at the horizontal and the vertical net forces. Once again, there's no acceleration of the car up in the up or down direction, so vertically all forces must balance. So now we've got that n cosine theta, which is the force acting up, must be balanced by now the two forces acting down. We've got mg, which is what we had before, but we've also now got the vertical frictional force, which is Ff sine theta. We've also got now horizontal forces, and again we've got two. We've got this force plus the horizontal frictional force. So now we've got that n sine theta plus the frictional force, which is acting in the same direction, the horizontal one, which is Ff cosine theta. That is going to be the force which provides the centripetal acceleration. So now I can get rid of those terms there. I've used those. This combination of these two forces is going to provide the centripetal force, mv squared over r. I'm going to solve for m in this formula here. I'm just going to rewrite this formula to say that mg is equal to n cosine theta minus ff sine theta. And that means that if I divide both sides by g, I get something for m. That's the mass. And now I can substitute this mass term into this here. So now I'm going to get that n sine theta plus ff cosine theta is equal to m, which is now this huge term, n cosine theta minus ff sine theta over g, times v squared over r. So we'll put v squared over r right at the end. And now I can remember that, let's just remind you that Ff, the frictional force, the maximum frictional force, is always mu n, the coefficient of friction times the normal. So I'm going to replace Ff in the two places where you find it. I'm going to replace that by mu n. And here, mu n. Now you'll notice that n features in all the terms, so that cancels. And now I've got for v squared, which is going to be the maximum speed that I can go round this bank turn, relying not only on the coefficient or the component of the normal force, but also the frictional force to provide my centripetal force. The maximum speed I can travel, given that of course the frictional force is at its maximum, is going to be given by this term here, which is sine theta plus mu cos theta, divided by this term here, which is cosine theta minus mu sine theta, and then you've got to bring the g and the r up here, so it's times gr, and that is the formula for the maximum velocity that you can travel around a banked turn without shooting off the top of the bank. And if we examine this for a moment, what happens again if theta is 0, that is to say if the road is absolutely flat, there's no banking? Well, sine theta will be 0, cosine theta will be 1, so you've got mu gr on the top, and then on the bottom cosine theta will be 1 and sine theta will be 0, so you've just got 1 on the bottom. So v squared equals mu gr, which is exactly what we showed a little while ago, that on a flat surface, the maximum speed that you can travel round a bend depends on the friction of the road and the radius of the curve. So what we've just shown is that if you travel around this curve and you're also relying on friction, you can travel up to a certain maximum speed and friction will stop you from flying off. But if you go any faster, then you'll just sail off the top of the curve, and that will be the end of that. But there's also a minimum velocity. If you go too slowly, then what will happen is you'll just slide down the bank. So we now need to find what is the minimum speed before you start sliding. Obviously, friction will stop you sliding up to a point, but when you've exceeded the maximum frictional resistance, you will slide down the bank. When does that arise? Well, once again, here is our banked surface at an angle theta. Here is the car, and it will have the force mg acting down. As before, it has a normal force acting up, and that normal force can be resolved into, just as we had before, n cosine theta vertically and n sine theta horizontally. That is exactly the diagram that we had before. And I'll just extend the road a little bit this way. Now this time the danger is that we're travelling too slowly, and consequently the car will drift in this direction down the ramp. So if that's the case, the frictional force that is acting to stop you doing that is acting now outwards, because it always opposes the direction or the tendency to move. So since there is a risk that you're going to go down the ramp, friction will act up the ramp. And once again, we'll be able to resolve that frictional force into a vertical and a horizontal component. And we'll just remind ourselves that the frictional force vertically is going to be ff sine theta, and the frictional force horizontally is going to be ff cosine theta. That's exactly what we had before. It's just that the frictional force is now acting up instead of down, and therefore the components of it will be acting upwards in the vertical direction and outwards in the horizontal direction. Once again, we can balance the forces in the vertical direction because there is no movement in the vertical direction. So now what have we got? We've got n cos theta plus the frictional force vertical component now acts in the same direction, and that is ff sine theta, and that's going to equal the only force now that's acting down, which is mg. What about the forces in the horizontal direction? Well, we've got n sine theta. Now it's minus. Last time the frictional force acted in this direction, the same direction as the n sine theta, but now it's acting outwards. So now we've got to subtract the horizontal frictional force, which is ff cosine theta. And what is that going to do? That is going to be the resultant force that will provide the centripetal force to keep the car going round in a circle. So that's going to provide mv squared over r. And just as we did before, we can solve this top equation by writing mg is equal to, well, we can see what it is, n cos theta plus ff sine theta. So if I divide both sides by g, then I'm going to get an equation for m, And again, I can substitute that value for m into this here, and so this equation becomes n sine theta minus ff cos theta is equal to m, which is n cos theta plus ff sine theta over g times v squared over r. Put a line there so it shows it's separate. And once again, as before, we remind ourselves that the frictional force is mu times the normal force, mu n, so we can replace frictional force here by mu n, and we can replace frictional force here by mu n. That was a plus term. And once again, you'll see that there is an n in all the terms, so that cancels out. And now I can write for v squared, which now, remember, this is the minimum velocity in order to stop the block from, or stop the car rather, from rolling down or sliding down the bank. This minimum velocity is going to be given by this term here, which is sine theta minus mu cos theta, divided by this term here, which is cosine theta plus mu sine theta, and then the g and the r have to come up here, so you get that term. And that now is the velocity for the minimum velocity as you travel around that bank. Any slower and the car will simply slide down the bank. And you'll notice that this formula is almost the same as the previous one for maximum, except that for the maximum velocity, this minus was a plus and this plus was a minus. You'll also notice something rather odd, that if theta is 0, that is if the road is absolutely flat, then what you've got here is sine theta, which of course will be 0, minus mu cos theta. Well, cos theta will be 1, so this whole top term will be minus mu gr. And then at the bottom you'll have cos theta, which is 1, and then mu sine theta is 0. So the whole thing becomes minus mu gr. So v squared, the minimum you can have, v squared is minus mu gr. Well, you can't have a minus square number. So what that essentially says is that the practical minimum is 0. That is to say that you can travel, when the road is flat, you can travel at no speed at all and you still won't slide. And that is of course perfectly obvious, because if you're on an absolutely flat surface, you're not going to slide anyway, because there's no force pulling you down. Now, having discussed banking for cars, we also just need to think about banking for aircraft, because this is exactly the same way that aircraft do their turns. Just think for a moment about the way an aircraft works. I'm not very good at drawing aircraft. Here's an aircraft which is travelling in this direction. What causes it to travel in this direction? Well, it's got an engine underneath which is shooting out. It's a jet engine, so it's shooting out gases backwards at a huge rate. And because conservation of momentum applies, if you've got a lot of fuel shooting out that way, the aircraft, in order to maintain momentum, will travel in this direction. But that doesn't tell you how it gets up off the ground. And the reason is that in travelling very fast in this direction, it hits air which hits its wing, and the wing is so shaped as to cause the air to be diverted downwards off the wing, and that gives the aircraft lift. And so it's the combination of moving at speed, thanks to the engine, in a horizontal direction, which causes the air hitting the wing to push downwards and thus give the aircraft lift in the upwards direction. So now here's my plane. I'm now looking at it head on. It's coming towards me. That plane will have a weight, mg, mass of the plane times g, and it will of course have a lift, which is what's keeping it in the air. And if the plane is travelling at a constant height, then obviously there's no change in the vertical direction, and consequently L will equal mg. Now what happens when that plane wants to turn a corner? Well, there's no friction. We can ignore air resistance for these purposes, and so what the pilot will have to do is to cause the plane to turn at an angle. So he'll have to dip the wings, or dip one wing, so that the plane is now at an angle, and the angle is theta. We've still got, of course, the force acting down is mg. The lift, of course, will always be perpendicular to the wings, so the lift is now in this direction, and we can, as ever, resolve that lift into two components. If this angle is theta, then you can show that that angle is also theta, which means that this is going to be, this component is L cosine theta, and the horizontal component is L sine theta. And now we do exactly what we did before. We say that since the plane is actually going to be at a constant height, when you're turning you tend not to change height, consequently the vertical forces must balance. So L cosine theta must equal mg. There are no frictional forces, we're not on a road, and as I say, we're ignoring air resistance for these purposes. And then the only horizontal force, L sine theta, which is this one, that's what's providing the centripetal force, and that is mv squared over r. And you can see that L is going to be mg divided by cos theta. So if I put that in here, mg over cosine theta, because that's what I get from here, that's for L. Putting that in for L there, multiplying by sine theta equals mv squared over r. And once again you'll notice that the m's cancel, and that means, and sine theta over cosine theta of course is tangent of theta, so that gives us that v squared is going to be equal to rg tan theta. And you may remember that that is exactly the same formula that we derived when we were looking at a car travelling on a bank surface where there was no friction. So since there's no friction here either, you get exactly the same formula. But now, of course, the pilot has, well, he can't affect g, but he can adjust v, r and theta for his own purposes. So depending on what angle he wants to bank the plane at, the radius of the turn and the velocity he wants to travel at, he can adjust all three of these to achieve the turn he wants. If it's going to be a gradual turn where r is very large, then he doesn't need to bank the plane very much, because if r is large, tan theta can be much smaller. On the other hand, if he needs to do quite a sharp turn, then r is much smaller, and that means tan theta will need to be greater, or v will need to be greater. So he'll either need to increase speed, or he'll need to increase the angle of the banking. And that is a matter of judgment for the pilot. That is causing a force in this direction, and that will result in a frictional force in this direction, and that's what causes the car to go forward. It is the friction between the tyre and the road that causes the car to move forward. The engine turns the wheel, but if this were frictionless, sheet ice, nothing would happen. It's because there is a frictional force that causes the car to move forward. So now let's suppose this is an overhead view and I'm travelling in a straight line, and here is my car, and my wheels, of course, my tyres are pointing in the direction of travel, and at some point I want to go round a bend, and that will be an arc. It will have a radius r, and when I get to this point here, if I want to turn, I'm going to have to turn the wheels. The bookcase will begin to move. Then the next thing I want to ask is, what makes a car go along a road? In other words, what drives it forward? Here's my car. Here am I driving. And the question is, what causes it to go forward? And you might say that the answer is the engine, which is usually underneath the bonnet. But that's not strictly true, because all the engine can do is to cause the wheels to turn. If this were a frictionless surface, if this were sheet ice, all that would happen is that the wheel would go round and round, but the car would not go forward. The reason that the car goes forward is because of friction between the surface of the road and the surface of the tyre. What is happening is that the wheel is spinning in this direction. Hello, today we're continuing in our series on A-level physics revision, building on the information we learned in the videos on circular motion and friction. And we're going to be looking at a subject which is included in some A-level equivalent courses on banked turns. I first need to remind you what we learnt from the video on friction. If you have a heavy block on the floor, such as a bookcase, which has a mass m, then from its centre of mass it will exert a force downwards, mg. And there will also of course be a normal force acting upwards, and the normal force always acts perpendicular to the plane of the surface. Now, if you attempt to move that bookcase by applying a force, let's just say initially a small force, to push it to the right, of course you know it won't move. And the reason it won't move is that there is a frictional force, which is the friction between the bookcase and the floor, which we'll call Ff. And that frictional force always moves in the direction to oppose the movement you're trying to achieve. So you push it in that direction, but the bookcase has frictional force which resists that force and pushes in this direction. And as you increase the force against the bookcase, so the frictional force increases. It's called a non-conservative force. It's always exactly equal to the force that you're pushing, subject to the fact that there is a maximum frictional force. And when you get to that maximum frictional force, that is the last point at which the bookcase can resist movement. If you increase your force to exceed the maximum frictional force, then the bookcase will start to move in that direction. And the maximum frictional force is given as the coefficient of friction, which is mu, times n, which is the normal force. And in this particular case, you can see that since the bookcase is not going to accelerate up or down, the net force in the vertical direction must be 0. And that means that n must equal mg, because n is going up, mg is going down. They must be the same so that the net force is 0. And so we can see that the frictional force maximum is going to equal mu mg. So when your force against the bookcase exceeds mu mg,